Hi everyone, this is Aarohi from Python Technologies, and in this video I'll explain what is ResNet. Specifically, I'll discuss about ResNet50 and will show you the ResNet implementation on a dataset with explanation of code of every single line. So basically ResNet is used for computer vision tasks like image classification, image detection and image recognition. So see, basically residual networks is similar to the networks which have convolutional pooling, activation and fully connected layers, right? Which are stacked one after the other. The only difference is that in residual network, there is an identity connection between the layers. Let me explain you. Yeah, let me explain you identity block now or identity connection. See what happened is, just see this picture. See, this is one layer, this is second layer, and this is third layer. So these layers are stacked one after the other, right? So means data from this layer will go to this layer and then this layer and finally we'll get the output. So this is how traditional network work. See, in ResNet, as I've just told you, ResNets are similar like other networks only, but there is only one change, like we are using identity connection in it. Now, what is that identity connection? So if you'll see this picture, this line from here, skip connection, and then data is the X value is going here. Means this is the initial X value, this is the input which is traveling through this network, and finally we are getting some output, right? So this input value, we are adding this input value to the output of the convolutional block. So this is a full block. This block have three layers. The output of this block is f of x, function of x, and in this function of x we are adding the actual value of x, right? So this is what identity block is, and this x value is skipping these connection and we are just directly giving this x value at output. So this is what identity block is, right? Identity block simply means we are adding the actual x value into the error. See, basically what I want to say over here is, simply we can say that if the network will learn from the difference between the input and output, then overall accuracy can be increased, right? So what I'm trying to say over here is, let me explain you in more detail, you'll understand then. See, what is intuition behind residual network, right? So the main intuition is we want to make output equal to input. We want to make output equal to input. That means, see, if output is equal to input, that means there is no difference between output and input. That means this is 100% accuracy and there is no error. So if input is equal to output, that means both the values are similar. There is 100% accuracy, no error is there, because X is input and Y is output. In normal networks, if I talk about normal network before residual network, how algorithm works? Algorithm learn on the basis of this Y value, right? Understand this very carefully. See, before ResNet, all the networks were learning from this Y value. But in residual network is learning from this f of x, is learning on the basis of error. So as I've just told you, if network will learn from the difference between the input and the output, then overall accuracy can be increased. And if error is less, that means y value input is more similar to y. If error is more, that means input is very much different from output. So how we can make output equals to input? So for that, over here, see, y is equal to x plus function of x. So this is what identity block is doing. Y is equal to fx plus x. X is means we are adding the initial value of x into our function of x. So, and our target is to make input equals to output. So how we can make input equals to output? Let's suppose if we make this function of x 0, if the value of f of x is 0, then y equals to x is, y is equal to x, means our target is to make this function of x is equal to 0, because if the function of x value is 0, then y is equal to x. So this is what we want to achieve. So in normal networks, as I've shown you, normally network learn from the value of y, right? But in residual network, we are learning from this difference of x and y, right? So this is the intuition behind residual network. Means our ultimate goal is we want to make y equals to x. We want to make input is equal to output, because if input and output is similar, that means there is no difference between input and output. That means this is 100% accuracy. Moving further, let me show you the data set. Let me show you the data set on which we are going to work today. So the data set is basically a room classification data set in which we are having three different kind of rooms, three different kind of classes we have. One is bedroom class, other one is dining room class, and third one is living room class. Means we have a data stored in three different folders, and one folder name is bedroom, and this folder have images related to bedroom, and second folder name is dining room. This folder have images related to dining room, and then we have third folder with the name of living room, which is having the images related to living room. So over here what I have done is I've imported all the required modules, and then in this line I have used a method list directory. List directory will give you a list of folders which are present at this particular location. So this location simply means I have a folder with the name of room dataset, right? In my PC I have a folder with the name of rooms dataset, and I want to see the list of directories which are present at this particular location, and then I have printed. So after printing I get these names. That means I have three different folders with the name of these things, right? So, and the type of, over here I'm checking the length. So length obviously we will be getting 3 because we have 3 different kind of folders over there. Now the next task is, what I want is, see over here as I've told you, bedroom have images related to bedroom, and this will have related images, and living room have the related images. Now what I want is, I want to store all the images from all the folders in a single list, and the list is rooms. This is a blank list right now. In this particular list I want to store all the images together in the single list. So for that I'm using a for loop. See, I'm using for loop. This is a nested for loop. Under this for loop we have another for loop. So the very first for loop, what this for loop is doing, this loop will enter in a folder, and after entering in a folder, the second loop will will get all the images of that particular folder, and then again when will enter in second folder using this loop. After entering in second folder, this loop will list all the images. This loop will get the list of all images from that particular folder. In the same way we'll enter in then third folder and we'll get the list of the images of third folder. So over here I'm printing this list, right? So see, this kind of data you'll see in that particular list. You are getting this kind of data. So first of all, this is a folder name, and then proper image path. This is the image name with proper path. See, so these are the folder names on this side, and these are the related images. So as I've told you, I want to store all the data of all three folders together. So this is the first folder in related images. If you scroll down, you'll see, let me show you, dining room and then the related images. So then you'll scroll down, you'll see the images of living room and then all the images of living room. So now we have a list with the name of rooms. That list have data of all the folders together at one place. Now what I want is, I want to store the folder name in a separate column and the image URL in a separate column. So what I am trying to do over here is, I'm creating a data frame by using pandas, and data which we want to give to a data frame, on which I want to create a data frame, is present in rooms list. So this is a room list name. So this whole data is present in this list, right? And columns, how many columns we want to create? We want to create 2 columns. In one column I want to store the room type, means room folder name, and in the second folder I want to store the proper image path. So these are the 2 column names which I want to create. So once we have created the data frame. So over here, I'm using a head method of data frame just to show you the record whether data frame has created or not. So you'll see this is the first folder name, column name, and this is the second column name. In room type column name, we have a folder name, and in image column name, we have related images. So over here we can say room type simply means the labels, class labels. So these images are belongs to this particular class, right? So we have, this is our y which we want to predict or classify, and this is our x input. Now what to do next? Now see, the next thing is, okay, let's see, I hadn't told you like how many total number of images we have in total. Let me show you that. So when you check the length of rooms underscore df, so you'll get 393. That means in total we have 393 images. See, I know this data set is very small, so why I'm using this small data set? Just to make you understand the concept, and I'm not taking a big data set because that will take so much time to process the outputs. So I'm just taking the small data set to make you explain that topic. So how many total number of images we are having? 393 in total, including all the three folders, and images in every particular column. So for that I'm using value count. So value count will give you the all unique values. So we have images belongs to bedroom 159, living room images are 148, and dining room images are 86. So if you total all these three, you'll get 393 in total. So this is the data set which we have. See, now the next task is, see, whenever you want to perform any computer vision task, the very first thing is to resize all your images to a single size. So this is what I'm doing over here. So I'm importing CV2. I'll be using CV2. By using CV2, I'll resize all the images. So over here, I have a variable with the name of IM size, and the size I've written over here is 224. So basically, this is a variable, and this is a image size. I'll be using this variable later on to resize my images. And over here, I'm having two blank lists, images list and labels list. Images list is responsible. In images list, I'll be storing all the images after resizing them, right? Means once I've done resize, I have resized all the images, I'll store all those resized images in this images list, and in labels list, I'll store all the corresponding labels. So for that, again, I'm using a loop. First loop will help us in entering in a folder, and with the help of second loop over here, you'll see, first of all, we are reading an image by using cv2.imread, and once we read the image, we are resizing an image by using cv2.resize. And what we want to resize, which image we want to resize, which is present in img folder, and what is there in img folder, the image which we have read by using cv2, and we want to resize this image to this size, IM size. That means 224 comma 224 means we want to resize all the images to a size 224 into 224, and then we are appending a images list. See the blank list which will store the resized images, right? We are appending a images list with the resized images, and labels list getting appended with the corresponding labels. And after that, I'm just printing the labels list just to show you how the result look like. So this is the result in labels. Obviously, result will store bedroom, dining room, and living room. So this is how labels are correct, right? Now, the next thing is images. See, now if I talk about images, so as we all know, computer understand images in the form of array. So we need to convert our images. Images is a list. All the resized images are present in it. We are converting this list into an array because computer vision in any computer vision problem, computer understand the numbers, computer understand the images in the form of array pixels. So we are converting it into the array, and then I'm just checking the shape of images. Now you'll see total number of images are 393, and the size of images are 224 into 224, and this 3 refers to RGB image, colored images, because we are working on colored images, so the number of channels are 3. So now in next line, I'm dividing this images, right? I'm dividing it by 255. See, this is not a mandatory step. This is just a this is just for your, mathematical simplification. The pixel intensity lies between 0 to 255, and 255 is the maximum number. So I'm dividing all the pixel values by 255 just to make the number smaller, right? So our images list is ready now. Our images are getting converted into array. First of all, what we have done, we have resized our images, then we have converted our images into array, then we have divided our image, array pixels by 255 just for mathematical simplicity. Now let's talk about this labels list. So if you've noticed, in labels list we have all the labels in the form of, alphabets, and computer don't understand alphabets. I mean, our algorithms don't understand alphabets. We need to, convert our data into a numerics. So for that we will be performing label encoding and one hot encoding. So after we have done one hot encoding, output would be like this: 393 and then 3. What is this 3? 3 means 3 different output columns. Why 3 different output columns? Because we have 3 kind of output labels: bedroom, dining room and living room. So we have 3 different classes. One hot encoding will give you the will give you the number of columns which are equivalent to the number of classes of your labels, right? So we are having 393 rows, 393 records, and we are having 3 columns. So this is a one hot encoded labels value. So now next thing is, let's divide our data into train and test. To with the help of training data, we'll train our algorithm, and on test data we can test our algorithm. See over here, the test size which I'm using is very small. Why I'm using very small test set over here? Because already our data set is very small, so I want to give more data to train my algorithm. So after dividing my data into train and test, I have just printed the shape of train and test records. So over here you can see I'm using 373 records to train the algorithm, and I'm using 20 records to test the algorithm. So this is all about our data set. Now you're clear about the data set. So this is basically a image classification, image detection problem, where we have 3 output labels: bedroom, dining room and living room. We will be training our algorithm on this data, and after training our algorithm we will give some unseen data, never seen data to our algorithm, and we'll see whether our algorithm is predicting correct results or not. Now let's start the ResNet algorithm. I'll implement this algorithm using Keras. So first of all, over here I'm importing all the required modules, and over here you'll see, first of all I'm importing all the layers from Keras.layer. I'm importing input, art, dense, activation, zero padding layer. I'm importing all the layers which are required for this algorithm, and then I'm importing Keras.models also for, by using this particular Keras.model we can create model and load models. And then I'm importing Keras.preprocessing. This will help us, doing some preprocessing on image, right? Like this, I have imported all the required modules. Now, as I've told you, like ResNet is similar like other networks, but with the but in ResNet there is only one difference, that we are having identity connection between the layers. So as I've shown you in the very beginning, like this is an identity block, and identity connection simply means this input is traveling layer from this layer to layer, this layer to layer, and finally we are calculating f of x. And this identity connection simply means that we are adding this actual value of x. Using this skip connection, we are adding this actual value of x in function of x, f of x plus x. This is the final thing. And the main intuition behind ResNet, as I've just told you, like we algorithm will learn on the basis of function of x, and our target is to make function of x is equal to 0. Then only our output would be equal to input. Right. Now over here you'll see how many layers we have in this identity block. 3 layers: first layer, second layer and third layer. Right. Now I'll show you the code of this identity block. So what I'm doing over here is, see, I am creating a function. Function name is identity block, right? and we are passing three parameters to it. I'll explain you all these features one by one, right? But just now, see, first of all, I will just give you an overview of this function, right? Identity block, then we'll go in deeper, right? So over here, you'll see first layer. This is the code for first layer. This is the code for second layer, and this is a code for third layer, right? And after this, all these three layers, what we are doing in a network, what we are doing in identity block, we are adding actual value of x with function of x, right? So after writing the code of three layers, over here you'll see I'm using add method, and what I'm adding x, and I'm adding x underscore shortcut. Now what is this x is, which is traveling from, the x simply means which is traveling from layer by layer, right? And what is this x shortcut over here? See, if you'll see in the beginning of this function identity block, I'm having one variable with the name of x underscore shortcut, and what I'm storing in this x underscore shortcut, I'm storing the value of x in it. See, why I'm storing the value of x in it? Because the value of x will change as the x travels from layer to layer, right? So, and in our final over here, we want to add the actual x value with the function of x. So I'm storing the value of x in a separate variable, so that we can have a actual x value stored in some different variable, and later on over here we can add x. X is now, what is x over here? X is a variable which is carrying f of x, and this x underscore shortcut is a variable which is storing the actual value of x, and we are adding both of them, and finally we are applying the final activation function on it. And what is the activation function we are using in it? ReLU. See, why we use ReLU activation function? Because if when you use ReLU activation function, what ReLU does simply, ReLU simply means it will transform all the negative pixel values to 0, right? And this will help you in this will help you, you'll not get the problem of vanishing gradients, because it will replace all the negative values with 0, right? So as you understand the basic structure of it, now let me explain you in depth what this code is actually doing. So till now we know that x shortcut is storing the actual value of x, which we will add this value later on in the final layer. And these three lines are the first layer code, these three lines are the second layer code, and these two lines belongs to the third layer code, right? And see, over here, okay, let me show you from the very beginning. So now the very first thing is we have three variable f1, f2 and f3, and the value which we are passing to this f1, f2 and f3 is in filters, this filters. Later on I'll tell you what is in it, but for temporarily let me explain you. See, this is the ResNet 50 architecture. The very ResNet 50 means we have 50 layers in our network. So when you will count all these things, you will get 50 layers. See, first of all, we'll be having one layer which will be having filter size of 7 by 7, and we'll run 64 such filters with stride 2. This is the first layer of our ResNet 50 architecture. And after that, we have one MaxPool layer, and the window size in MaxPool is 3 by 3, and we are using stride 2, right? So after that, over here, if you'll see, oh, here and here, if you'll see, we have layers in the pair of 3 layers, right? So because why we are having the layers in the pair of 3 layers? Because we are going to use identity block, and in identity block, how many layers we have in identity block? See, 1, 2, 3, right? So over here in this layer architecture, we are using layer in the group of 3. So the very first layer in the identity block, we will use a filter size of 1 by 1. And how many such filters we want? 64 filters. And in the same way, second layer of identity block will have a filter size of 3 by 3, and we are going to have 64 such filters. And the third layer of identity block will have a filter size of 1 by 1, and we are going to have 256 such filters, right? So this is the first block. Into 3 means this same structure will repeat 3 times. That means total we are going to have 9 number of layers. This grouping into 3, that means we'll have the same code thrice, right? Over here into 4 means we'll have this layer structure, this grouping of layer, how many times? 4 times. Into 6 means this these parameters of layers, we will be having these particular 3 layers how many times? 6 times in a network. So this is again 3 times, and if you'll add all these layers, you'll get total number of 15 layers, right? So as I just told you, just remember this one by one. First layer will have 1 by 1 filter size, second layer will have 3 by 3 filter size, and third layer again will have 1 by 1 filter size, and the number of filters in first 2 layers are same, and in third layer we are going to have 256 filters, right? So this filter is that basically. So now what we can say, that in F1 we can say that in F1, what value will go in what F1? 64. And in F2, which value will go in F2? This 64. And which value will go in F3? This 256, right? So why we are not providing values directly from here? See, we are using this filter. So this filter value later on we have mentioned like how to assign values to it, but for your understanding I have written over here that F1 will have 64 layers, F1 will have 64 filters of size 1 by 1, F2 will have 64 filters of size 3 by 3, and F3 will have 256 filters of size 1 by 1. Clear? And this x shortcut variable is again clear to you. This variable is used to store the actual value of x, because this x value will change when we use this x value in our architecture. So now the task is to write a first layer. See, what we are doing is over here, if you'll see x in x over here, x over here, x over here. See, what we are doing is we are updating the value of x. We are not using separate variable for every line of code. So what we are using, we are updating x value in every line of code. So the very first thing is over here in x variable, what I'm storing is I'm creating a con2d layer, right? Convolutional layer. And this convolutional layer will have how many filters? Filters F1. And F1 having common filter 64 filter. Kernel sizes 1 by 1, as I've just shown you. Filter sizes 1 by 1. Over here the value is 64. Over here kernel size is 1 by 1, and stride is 1 again. See, I have used padding valid and padding same in this whole code. So if you are not aware about what is padding same and padding valid, so in the comment section I have added a link which will explain you about this padding same and padding valid with proper examples, so that you will have a proper understanding why I'm using this padding valid and padding same, right? So I'm using padding valid over here, and this is the input which we are providing to it. And what is this? This is the value from here, the actual input value, right? So once we have applied these many filters, see in this ResNet network, in second after every convolutional layer we perform batch normalization. So over here we are performing batch normalization, and axis 3 simply means we want to perform batch normalization on output channels, right? So how many output channels we have right now? 3 output channels, RGB, colored image, right? So we are performing batch normalization on axis 3. Axis 0 is rows and axis 1 is column. So axis, in the same way, this axis 3 means the this output channels. And what is the input to this? Again, x is the input to this layer. And which x is this? X from the previous layer. The output of previous layer will become the input of next layer. Again, we are having x variable, and then we are performing activation function on it, and ReLU we are using. As I've explained you, ReLU will help you out in you will not have a problem of vanishing gradients, because if you'll use tanh or other activation function, they will give you a problem of vanishing gradients. ReLU will replace all the negative values with 0, and over here we are using ReLU activation function. So this is the task of first layer. Now let's talk about the second layer. So what are the dimensions? What are the parameters second layer is having? So filter size is 3 by 3. And how many filters? 64 filters. Let's see how to write it. So creating convolutional layer again. So filters, how many filters we want to have, which are stored in F2, and what we have in F2? 64, right? Kernel size is F comma F. F simply means from here filter size is F. See, in our whole this layer structure, you can even write 3 comma 3 over here. So the value of F is later on we are getting this value of F, but for your understanding, just understand over here the kernel size is 3 comma 3, and this F later on, this F will provide the value of 3. So right now just assume 3 comma 3 over here. Stride is again 1, and padding, as I've told you, go through the other tutorial which I have shared, and you will get to know what is it. And then again we are doing batch normalization, and then again we are performing activation value function, right? So this is the code of second layer. Now let's talk about third layer. Again in third layer, let me show you the code for third layer. Third layer will have filter size of 1 by 1, and how many such filters we want? 256 such filters. So let's see how it is working. So we have created a convolutional layer. Number of filters is equal to F3, and in F3, what is the value in F3? 256, right? And kernel size is 1 by 1, and stride is 1 by 1, and again we are doing batch normalization. See, over here the important thing is to note. So see, in the very first two layers, we are, after batch normalization, we are performing activation function. But in third layer, after batch normalization, we are not performing ReLU function. Before performing ReLU activation function, we are adding the actual value of x, which is stored in x shortcut, and the f of x, the output, which is stored in this x. We are adding them, right? So this is the, after adding this x into f of x, we are applying the activation function, ReLU function, and then we are returning a x, right? So this is how our identity block works. So if you remember, you can see over here. So after third layer, before performing this activation function, we are adding f of x plus x, and then we are performing the activation function of last layer. So this is what identity block is, right? So now I hope this is clear. Now let's move further. There are other aspects which we need to take care while creating this identity block or while using this identity block. Now always remember, see, if the input size of image and the output size of image is same, then we can use identity block. So what I mean to say is the input which we are giving to our network is, let's suppose the input is 224 into 224 into 3. And while this input is moving from layer to layer, and after completing the whole task, if the output size of if the output volume is 224 into 224 into 3, input is again same and output is same, means the input size of the image and the output size of the image is same, then we can add the actual x value into f of x, right? Means identity block will work when the input size of the image and the output size of that particular block is same, then only we can add this x into f of x. But let's suppose if the size is different. Let's assume the input which we are giving to our network is 56 into 56 into 64. This input is first moved to this layer, and from this layer to this layer, and after this layer to this layer. And let's suppose after moving after this input moved from few layers, the output size is 28 into 28 into 128. Let's assume this. Now the input size of image is different and the output size of image is different, right? So in this case, we can't use this identity block, right? That simply means we cannot add this x value into f of x. Why? Because the input size of the image and the output size of the image is different. So what to do now? So if you see over here, if you'll observe, I have added one layer in this shortcut path. Right. So this is basically called convolutional block. See, convolutional block will help us to add the input with this output when the input and the output image size is different. So you'll see we have rest of the task is similar. These three layers, and this is the shortcut connection. This is how identity block looks like. But there is only one difference. See, we have one more convolutional layer over here. Let me show you the identity block again. See, in identity block, we don't have any layer over here, right? Because the input size and the output size of the image is same. But over here the input size and output size is different, and this is a convolutional block and identity block is similar. There is only one difference, like in convolutional block we have one more convolutional layer in between the shortcut connection, and the task of this convolutional layer is to make the size of this input equal to the size volume of this output. Right? Clear? Why we are using this convolution layer in between shortcut path? Because we want to make the size of this input equal to the size of the output, so that we can add this input to the output. Now how this convolutional layer will make the size of this 56 into 56 into 64 to a 28 into 28 into 128. So there are two options for matching the output size. Either we can pad the input volume, or we can perform the one by one convolution. Don't worry if you don't understand, I'll explain you how to do it. So I'll show you, I will resize this image to this size by using the second method, by performing one by one convolution. Let me show you how to do that. So this is the input size and this is the output side, and what I've just told you, like I'll use one by one convolutional over here to make this size equal into this size. And if you're familiar with this formula, n plus 2p minus f by s plus 1 into n plus 2p minus f by s plus 1. So CNN is using this formula to CNN works on this formula. So n is the image size. So what is the image size over here? 56 minus, so this one, okay, over here we'll not use plus 2p. The formula over here is n minus f by s plus 1. Sorry, there is a mistake. There is no, the formula is n minus f by s plus 1, right? So because we are not using padding over here. So this p stands for padding. So n is 56 over here and minus 1, this f means filter size, and what I've told you is we'll use one by one filter size. So the size of filter is 1 and stride is 2 plus 1. So when you solve this, you'll get 28. In the same way, in this side also you'll get 28. So the image which is of 56 into 56, when we pass this image from this convolutional layer, this convolutional layer is performing a one by one convolutional, and by using this formula our image size became 28 into 28. Now the size of this and the size of this is same. Now we can add it. So always remember. Now let me show you the code of this particular thing. Right. See, identity block and convolutional block is doing same thing. The only thing is both identity block and convolutional block are responsible to add the actual x value into a function of x. The only difference is we'll use identity block when the input size of the image and the output size of the image is same, and will add x into f of x by using convolutional block when the input size of the image is different from the output size of the image. Now let me show you this convolutional block with the help of coding, as I've just shown you how to use identity block. So this is the convolutional block. Again we have a function convolutional block. Again these are the required parameters. F1, F2 and F3 will get the values of filters. Which filters I'm talking about? Means how many filters over here, if you'll see over here. So in the very first block we have filter size of 64, F1 we have 64, F2 have 64 and F3 have 256. And if I talk about this block, F1 will have 128, F2 will again have 128 filters and F3 will have 512. And if I talk about this block, F1 will have 256 filters, F2 will have 256 filters and F3 is 1024. So these are F1, F2, F3, right? So over here, So again, X shortcut is storing the actual value of X, because later on the value of X will change and we want to add the actual value of X at the last step. So we are storing it in a separate variable. So again, see, first layer, second layer and third layer. Task is again same. The whole code is similar. See, the only difference will come over here. After in identity block, what we are doing after third layer, we are directly performing this code, right? We are adding X with X shortcut. But over here, we have a layer in between. Remember this layer, right? Before adding, we are we have written the code of first layer, then we have written the code of second layer, then we have a code of third layer, right? So before applying, before adding this with this, there is one more layer. So this is that particular layer, right? So this is that particular layer, and the thing to remember over here is which technique we are using over here. We are using one by one convolutional. So this is a filter size one by one convolutional layer over here, and stride S is storing 2. Stride is 2 over here, right? Stride is 2. So after doing that, we are adding X with the function of X, and then we are applying the activation function. I hope the convolutional block and the identity block code is clear now. Now let's start with the ResNet algorithm. See, till now we hadn't created ResNet. We are just preparing the two functions which are required while creating ResNet: identity block and convolutional block. Convolutional block will pass the input to the output when the input and output size volume is different, and identity block will pass the input when input size and output volume is similar. So this is the ResNet50 model. So the very first thing is of this ResNet model is we will perform 64 filters of size 7 by 7, and this /2 simply means stride 2. Now let me explain you why we are using stride 2 in a network. So if you look at the first operation of each layer, we are using stride is equal to 2 instead of stride 1 like for the rest of them. So over here, first of all, if you'll see over here, okay, let me tell you over here. See, 128 by 2, that we are using stride 2 over here, right? And this is the first operation of a layer. And then if you'll see this layer again, over here, the green one, over here again, I have written 256 by 2. That means we are using stride 2. This is again very first operation of next layer. In the same way, over here also 5 and 2 slash 2 means we are using stride 2 over here. This is again a first operation of that particular layer. So what I'm trying to say over here is we are using stride 2 at the first operation of each layer. And if I talk about rest of the layer, see, if you'll see over here, we are using 128 only. That means we are using stride 1, right? So that simply means wherever you get this /2, we are using stride 2. Otherwise, in rest of the layers, we are using stride 1. Now, this means why this stride 2? So this stride 2 means that the size of the image is getting reduced in the whole network by increasing the size, by increasing the stride, instead of using a pooling operations like in normal CNN network. What we do, if whenever we want to reduce the size of the image, what we do? We always use MaxPool layer or average pool layer. Pooling layer is always responsible to reduce the size of the image. But in this ResNet, most of the time we are using stride 2 to reduce the size of the image. Or what we can say, see, if you see this network properly, so we are using pooling layer only twice. Once in the starting, over here we are using 3 by 3 max pool layer, and at the end, the very end over here, we are using average pool layer. Instead of these two operations in a whole network, we are using stride 2. So now, as I've told you, the very first layer of this network is having 7 by 7 filter size. And how many such filters we have? 64 filters. And then after that, we have 3 by 3 max pool operation with stride 2. So let me show you with the code this thing. So I have created a function ResNet50. See, basically this ResNet50 is a function in which we are going to implement all the 50 layers. Means I'll show you the code of all 50 layers of ResNet, how to implement this algorithm. This is the important function to know about. So while defining this function, input shape is 224 into 224 into 3. That means this function will accept the input image with a shape of 224 into 224 into 3. And how many output labels we have? We have 3 output labels. How? We see, this is an image classification problem, and we have three classes. One is dining room, other one is bedroom, and last one is living room, right? So that's why I've written 3 over here. So if you're working on a different data set, so you can write the number of classes as per your data set. And over here again, if you want to use some other image size, so you need to resize all your images to that particular size, and over here you need to give that particular size. All right. So in this string particularly, I have shown you like how this ResNet convolutional network will work. So first of all, what we have convolutional layer. And always remember, whenever we are using ResNet, so we are using convolutional layer followed by batch normalization and then ReLU. So whenever you're using convolutional layer, that means after that we are going to use batch normalization, and after that we are going to use activation function ReLU, right? So as I've just shown you in this particular image, first layer have convolutional layer, and this layer will have 7 by 7 filter size. And how many filters we are going to run on this? 64 filters, and stride is 2. So this is the first layer. This is the first layer, right? Okay, let me explain you this first layer, then I'll explain you these two things which are above this layer, right? So x is a variable. Again, we are going to update the x variable, and over here I have created a convolutional layer. Con2D, we are directly calling this Con2D from Keras, because in Keras we have this built-in layer, so we are calling that particular layer. So we want to create convolutional 2D layer, and how many filters we want to have? 64 filters, and 7 by 7 is the size of the filter, and stride is 2 horizontally and vertically, and this x is a input to that particular layer. And as I've just told you, we will be using batch normalization after that, and then we'll use activation ReLU function. So after that, we are using MaxPool layer with a 3 by 3 slide window size, and the slide is 2 by 2. So these two operations are the very first two layers of your network, this 7 by 7 convolutional layer, and then 3 by 3 MaxPool layer. All right. Now, after that, see, we have a layers in a group of 3. So, over here, from this particular point, we will be using identity block or convolutional block. So, as I've already told you, we will be using identity block when the input to this block and the output of this block have similar volume, right? If the input volume and the output volume of this block is similar, then we'll use identity block. And if the input volume and the output volume of the block is different, then we will be using convolutional block, right? And what is the main reason behind using identity block and convolutional block? The only reason is we want to add the actual value of x into f of x, and we want to make f of x is equal to 0, so that y becomes equal to x, right? So now these two layers I've shown you the code. Now let's talk about this. Okay, before moving to this particular part, as I've just told you, like these two line of codes I've written over here, what is it? So this X input is responsible to handle the input. It will accept the input with the input shape, and then after getting the input and storing that input in X input, we are doing zero padding on it, and we are doing zero padding of 3 by 3. Now what is this zero padding? Let me explain you this zero padding first of all. So for that I have a picture. I'll explain you that with the help of picture. So our image size is of 24 into 24 into 3. So we are doing zero padding on it. Zero padding of size 3 by 3 means 1, 2, 3. 3 rows we want to add 3 zeros on this horizontally and vertically, means all side of the images we want to add 3 times 0. Now what is the benefit of this zero padding? So zero padding means that the input volume with zeros around the border. So this is our image. So we are increasing the input volume by adding zeros on all sides of the image. We are applying this zero padding because when we apply convolutional layers, the size of the size of your volume or size of the image will decrease faster than we would like. Means, let's suppose we are not using zero padding. When we are not using zero padding, then what happens sometimes is that the size of the image, because we are using multiple time convolutional operation, right, in convolutional neural network. So what happens is when you are not using zero padding, the size of the image get decreased faster than we would like, right? So if you want to preserve the information, right? So what we want is basically whenever you want to preserve the information in the early layers, in the starting layers of your network, so that we can use low level features also, right? If you're not using zero padding, then you cannot access low level features. So suppose if you want to access low level features, then we can use zero padding on the borders of the image. By applying zero padding, we are increasing the image pixels, we are increasing the size of the pixels by putting zeros on the side, right? So this is what zero padding is. So now we have an image of 224 into 224 into 3. So we have applied zero padding on all the sides. That means this width and the height got increased by 6 pixel. 3 pixels on this side and 3 pixels on this side, and the same way 3 pixels over here and 3 pixels over here. So we are increasing height and width of our image by 3 pixels so that we can access low level features also. That's why we are using zero padding. So this is optional. If you want to use, if you want to access low level features, then you can use zero padding. All right. So after that, I've explained you this first two, convolutional layer and MaxPool layer. I've already explained you. Now the next task is over here. Now we will, from here now we will be using convolutional block or identity block, right? So what we are using over here is, let me show you that. So see, over here in x variable, I'm calling convolutional block. So if you remember, we have created two function, identity block and convolutional block, right? So over here we are calling convolutional block, right? Convolutional block simply means the input which we are going to our network would be different from the output of our that particular layer, right? So convolutional block is responsible to make your input volume equal to your output volume, right? So convolutional block. So let's go back to convolutional block. Let me show you convolutional block. So this is how convolutional block work. How many layers are there in convolutional block? We have 3 layers in convolutional block, and we have 1 layer in shortcut path, which is responsible to make your input equivalent to your output volume so that we can add x into f of x. So three 3 layers, okay, and fourth layers is in a shortcut path. So let's go to the function. So this is the convolutional block function, and this is the first layer, this is the second layer, this is the third layer. So when we are calling this convolutional block over here in ResNet block, over here. So when we are calling this convolutional block over here, that simply means we are implementing 3 layers over here. Means this. See, for giving you a proper idea, I have copied a code from convolutional block and I've pasted it over here so that you will get an idea like how this network will actually look like. So instead of this line, you can also write this line. Means this convolutional block function is carrying these 3 layers. Okay. And convolutional block, and we are passing the parameters. See, these all are the parameters which are required while defining a convolutional block. We have mentioned all these parameters, x and then f and then filters. So x over here, and the value of f is 3 and the filter size is 64 comma 64 comma 256. What this means is, so the very first layer, how many filters are having? 64, 64 and 256. If you remember, while teaching you, while telling you about identity block, I've told you, let me show you. I've told you over here that the value of F1, F2 and F3 will get later on from the code. So this and F1, F2 and F3 equals to filters, right? Now what this filters is, I've told you, like we'll define later on. So in ResNet over here, see in ResNet, see these are the filters and we have defined the values for filters. This will go to F1, this will go to F2 and this will go to F3. And F value of F is 3 over here. So that means what will happen? Over here, see, these are the 3 layers of convolutional layer, right? So I've just pasted those 3 codes over here and I've commented it out. That means I'm just giving you an idea how this network is working. That means if you're calling convolutional block over here, that means we want to run these 3 layers over here, right? And these are the different filters we have applied. And the very first layer will run with the 1 by 1 kernel size, and second layer will run by using f comma f. That means 3 comma 3, 3 comma 3. See, the filter size of first layer is 1 by 1, filter size of second layer is 3 by 3, and filter size of third layer is again 1 by 1. And these are the number of filters which we have defined over here, right? So now 3 lines work has been done over here. After that, we are using identity block. Now, why we are using identity block? We are using identity block over here because the output which we get after this 3 lines, the output means which will become the input of this block, and the output of this identity block is same. So means when input and output size is similar, then we use identity block. And over here again I have given the number of filters. Now this time which filter we will use? This is the value for F1, this is the value for F2 and this is the value for F3. In the same way, we are after running, and these are the 3 layers which are there in this identity block. Means 3 layers, and after 3 layers we have completed 6 layers. So again after that we are using identity block. That simply means that the size after this, after the completion of this work, the size of the image means the input of this block, the input which the output of previous block which will become the input of this block, and the output of this block, input of previous block and output of this particular block is similar. So that means we are going to use identity block, and over here again we are telling that this is the filter size. See, in the same way we will run our network. See over here I've shown you how to do that. So we are running a network like this. And okay, let's go back to the image. Let's go back to the image. See, we are running this whole architecture. Over here you can see, first of all we are running convolutional layer, this convolutional layer. Then we are running batch norm and ReLU. I have already told you that whenever you are running convolutional layer, we will be running batch normalization and ReLU with it. So these first 3 things are related to this very first layer. Then we have MaxPool layer, you can see over here. Then we have convolutional block. If you remember, after this input and zero pending and after this MaxPool layer, which block we are using? Convolutional block. And then we are using identity blocks. So let me show you over here. After using convolutional block, we are using identity block twice, right? That means 6 layers, three group of 3 in one identity block. There are 3 layers in one group. Okay, so again after that we are using convolutional block because size is different, and then again we are using identity block thrice, and then again convolutional block, and then again identity block 5 times, and convolutional block again identity block 2 times, right? So see, if you are getting confused, sometime we are using convolutional block and sometime we are using identity block. So just remember the logic. Whenever the input size of the image and the output size of the image of every any layer changes, we will be using convolutional block, and if the input volume and the output volume is similar, we will be using identity block. Next is average pool layer. Now after these all layers, what we have is average pool layer. So this is the average pool layer. Over here again we are using stride 2, which will reduce the size of this image, and we are even using average pool over here. After that we are having a fully connected layer. So this is the last layer. This layer, let me show you from here. After this whole process, after this average pool layer, see, before before moving to fully connected layer, so we are flattening the image. The image which we have till now is in a two-dimensional, three-dimensional image, but whenever we want to perform any classification task, so we need to convert our two-dimensional or three-dimensional images into a one-dimensional vector. So we are flattening the image over here, so that will become a one-dimension vector now. After that we have a fully connected layer, and how many neurons we have in this layer? So if you remember in classes, how many classes we have? So over here you can see that how many neurons we want to have? 3 output neurons. Why? Because we have 3 output labels: dining room, bedroom and living room, right? And which activation function over here we want to use? We want to use softmax activation function. And after that, see, this is just a name, we have given a name to this layer, that's it. After that, in a model variable, I'm creating a model, and input to this model is present in x input. If you remember, the very first line of this function is x input, right? The input to this network is this x input, and output will be this x is our output, right? And name of this model is ResNet50, and then we are returning a model. Now we have created a function. Now the time is to use that function. So in a model variable, I'm calling this ResNet50 function. So if you remember, the function name is ResNet50. Over here you can see function name is ResNet50. We are calling this function, right? So we have created a 50 layers architecture. Now we are calling this function, and the input shape is, we are telling our algorithm that input shape should be of 224 into 224 and should be a colored image, and number of classes are 3, output labels are 3. And then we are compiling a model, and the optimizer we are using is Adam optimizer, means our weight will get updated by this or Adam optimizer. After that we are seeing a model summary. See, when you are seeing a model summary, it is telling us that it will accept the very first layer, input is of 224 into 224 into 3. After applying 0 padding, the dimension will become 230 into 230. Remember, 633, this over here you can see 3 from this side and 3 from this side. Same way, 3 from this side and 3 from this side. From 224 to 224, our image will become 230 to 230 because we have added 0 padding in it, right? So, okay. After that, we are having image size got reduced to 112 to 112, and the number of output channels are 64 now. So previously our original images of this side and number of channels are 3. But after going through the convolutional layer, the size become this and we have number of channels this. Let me show you how we'll get this. I'll show you mathematically. See what is happening over here. The very first layer is of, see, this is the layer structure. The very first layer have convolutional, this filter size of 7 by 7, and how many filters we want to run? 64, and stride is 2. So this is the formula: n plus 2p minus f by s plus 1 into n plus 2p minus f by s plus 1. N means the image size. Our input size of image is, which is the input to this first layer. The input image which user will give will become the input to this layer, and the size of that image is 224 into 224 into 3. So n is the input size of image. So n means 224 plus 2 P means padding, and the padding we are using in first network is 3 minus F. F is a filter size. So what is the filter size? 7 by S. S means stride. What is the stride we are using over here? 2. So if you'll solve it, you'll get 112, and on this side also you'll get 112 into 64. Now why you are getting this 64? We are getting output channel as 64 because we are using 64 filters on it, right? Of this side. So it always, this number of channels, the depth of the output will always depend upon the number of filters you are using. So if you are using 64 filters, so the output depth, output channel will become 64. So this is how you are getting this. Clear? Now after that, which layer we have after that? We want to use 3 by 3 MaxPool on this particular layer. So the output of this will become input to this, means the image which will become an input for this MaxPool is 112 into 112 into 64. So again we'll apply the same formula. 3 by 3 MaxPool with stride 2. So again we have applied same formula, and what we got, size got reduced from 112 into 112 into 64 to 56 into 56 into 64. So what I'm trying to say is, after first and second layer only, our image got reduced from 224 into 224 to 56 into 56. By applying this formula, every layer will decrease the size of the image. So this is the basic maths behind the ResNet, right? So this is how, as I've just shown you the calculation, this is how the calculation will go on. And this is the model summary. After the model summary, we can train our network. Now we are training our network. We can directly use fit method, and we have already divided our data into train X and train Y, and how many epochs we want to run. I'm just running 3 epochs because I want that it should get processed soon, and I can show you the results. And the batch size is 32 right now, right? So after running 3 epochs, how much accuracy we are getting? We are getting 38% accuracy. See, I know the results are very bad. Why we are getting so much bad result? Because the data set is very small. In total, we have around 400 images, right? 398 or something like that. We have that much images. The data is very small. So if you want good result, data set should be, a big data set. So after training our algorithm, we are just testing our model by giving this, and this is showing us 40 on test data. It is showing us 44% accuracy. Now let's test our algorithm on unseen data, means we have given some never seen data to our algorithm, and let's see how our algorithm predicted. So first of all, let's suppose this is an unseen image, and we have load the image. So the very first thing is, you need to resize that image to 224 into 224, because our algorithm will accept that input image only. So if the size of the image is different, your algorithm will give you an error. It will not accept the input, right? So it is mandatory to resize your image into 224 into 224, right? And after loading the image, we need to convert our image into an array, because computer will understand the image in the form of array. So that's why I'm converting it into a array. Then we are expanding the dimensions. We are pre-processing our input image, and after that I'm printing the shape of image. After that, you can see that our image shape is 224 into 224 into 3. Now this is how our model is predicting. Model dot predict X. What is in X? X, in X only we are having a processed input. So this is saying that input not belong to first class, input is not belong to second class, it belongs to third class. Which is a third class? A third class is dining room. So this image belongs to a dining room class. So this is how ResNet works. Thank you.